Okay, so going to look at the first method of solving a harmonic oscillator. This is the easier method if you are comfortable with operators. So just to go over operators really quickly, it's just a way, a different way of, say, looking at an operation here. So you could have something like, say, n plus 2n, and I could look at that as, you know, for every n I am going to add 1 and then plus 2. So I could define something like that. If I'm going to do it over and over again, I could just go ahead and call that an operator. So any sort of operation, you know, A plus B equals C, this can work as an operator. The way that we've been using it is like here in our Schrodinger equation. We have this idea. Our Hamiltonian operator is h bar over 2m d dx plus the potential. My Hamiltonian operator acting on psi is just this guy. So h bar over 2m, and then the second derivative, and then the potential acting on psi. So in this case, our order does matter. This operator is going to act on this wave function. So I'm taking the second derivative of the wave function with respect to x. That's how we get things like when, say, we're taking the expectation value of the Hamiltonian. What I have is this Hamiltonian is acting on this psi. It is not acting on the complex conjugate, however. So we did that explicitly in problem 2.10, and that's how we get the result that we did. So for operators, the order does matter. It's just a way of writing like a shorthand for this function. So we can just define it to be what we want. In order to get the energy, the kinetic energy from the wave function, I have to multiply the wave function by negative h bar over 2m and then take its second derivative. Sometimes it's easier to just write that out in an operator form. We do the same thing for momentum too. So in this part, we're going to be coming up with some other operators. Specifically, they're going to be ladder operators. So the first idea is just to rewrite our Schrodinger equation like this. So all you do here is just multiply out that 1 over 2m. So we're just multiplying that guy out. So I have 1 over 2m. I could call this negative I, or I could just do it 1 over I. So I can take those guys squared, and then I have a omega and an x, and both of those are squared as well. And and then that's times psi, and then times E of psi. So we're just rewriting this guy in a way that's a little bit, as he says, more suggestive. So I'm taking the square root of this and the square root of this, so that we can see that if these were numbers, this is not a number, this is an operator. This is a operation that we perform on something. So this is not like some distance d over distance d times displacement x. This is taking an operation, which is specifically the derivative. I square the derivative operation and I get the second derivative. If they were numbers, this would be easy to break apart. So you have u squared plus v squared. I could break that, you could factor that into u minus iv times u plus iv. However, we're not dealing with numbers. Like I said, we are dealing with operators. And order of operation can matter in an operator. Another way to say that is commuting. So a lot of operators don't commute. In particular, something with a derivative is not going to commute. So u times v is not the same as v times u if we have an operator, or at least not necessarily. So, but we can use that too. We can still use that idea. We can still use this idea to break it apart into something that is maybe more useful. And we can look at the idea of a plus and a minus. So what we're looking at doing here is just breaking apart this guy into a u and into a v. Oh, and I realize now that I think I left out a mass term there. I did. Oops. Probably should have checked those units. There we go. There we go. That's better. Okay. So breaking that apart, taking the square root, we get 1 over square root of 2m. And then we can have our square root. So like our u and our iv. So we had that term squared, so we just take the square root of it, which is easy. That's just h bar over I d dx. We have two solutions here. We have a plus and minus, m omega x, and we're looking at u, and then we need iv. So just put the I out in front there. So we can call that a plus and a minus. So just going off of our general idea here, that if I had numbers, I would be able to do this with them, right? But I have operators. Oops, I don't have numbers. So if I go ahead and FOIL that out, I get u squared plus ivu minus IVU, and then we get negative V squared, and those guys cancel. Just using that same very simplistic idea to come up with these two operators to see if I can then apply them to my equation. So here, I guess I should write that as U squared, and then this would be something like V squared. So I just want to write it in that format. However, you may notice that this is not going to work out as nicely as that guy. So let's take a look at what happens if we do this. So I have my A plus operator times my A minus operator. I'm just going to write them both out explicitly. So I have 1 over square root 2m times h bar over I d dx plus, I did plus first, I m omega times x, and then that's going to be multiplied by 1 over square root of 2 h bar over I d dx minus I m omega x. Make sure I copied that down right. Yep, looks like I didn't miss anything, so good. Now, he does make a recommendation in Griffiths, which is not a bad idea, actually. Which is, he does say it might be helpful to just throw in a function fx, so you can make it clear what your operator is working on. So for example, when you get the difference between fx times ddx versus ddx fx. In this case, I have to take the derivative of my function fx. In this case, I am not taking the derivative of my function fx. So that's actually pretty good advice. So I'm going to go ahead and follow it and just throw in that function fx. So I have the multiplication of my two operators just acting on a function. I don't care what the function is, I'm just putting it in there so it's easier to keep track of. Okay, so those two constants multiply together, I get 1 over 2m. And I have this guy, h bar over I d dx plus I m omega x times h bar over I d dx minus I m omega x, and then acting on this function f of x. I'm going to go ahead and act out this operator acting upon that function. Oh, I suppose I should write it on this side too. So it's a plus operator, leave little hats for operators, times a minus operator acting on f of x. This guy's over here. And now I'm going to have these acting on f of x, just the same way that these guys act on psi. So I get h bar over I times the derivative of f of x minus I m omega x times my function f of x. Now we can go ahead and do our good old FOIL. Oh, totally forgot to write that part in there. So I have h bar squared over, I'll just write it as I squared, but that's going to be -1 ddx squared acting on f of x. So I act this operator on the left onto this one from the right, and I get the second derivative acting on my function. So I take now the second derivative of my function f of x. Then I get minus, my i's cancel out, h bar m omega, oops, well yeah, we can put those out in front, that's fine, h bar m omega, and then I have ddx acting on x, f of x. Now we do our insides. Again, my i's are going to cancel out, but now I have m omega h bar x, and then the derivative of f of x. And then we'll get minus I squared, which is -1, so minus minus is a plus, m squared omega squared x squared acting on f of x. Let's see if I managed to do that all right. Yeah, actually, that's surprising. So it's the same result we have here. It might be easier to see how he did it. Well, I mean, it's typed, so obviously it's going to be clearer. So we get h bar and then over I squared, so that ended up being that -1. And then that is times the second derivative of x, so you act out that operator twice because we had this guy times this guy. So that's the second derivative of x. Then we had this guy. Well, actually, I think he did, yep, this one next. Yep, he did the normal way. So then we get the i's cancel, we get h bar over m omega, and then we get the derivative of x times the function. However, when we do these terms, we now have x before you take the derivative. So this is how we get this non-commuting property, because this one you take the derivative of x, this one x is outside the derivative. And then we have our last term there, which there's no operation on it. Then we can go ahead and simplify that out a little bit. We can pull out our x, so you can always pull out that test operation at the end, make your life a little bit easier. Let's do -h bar second derivative on f of x. Oh, you know what, I'm going to pull out my f of x, so let's just say second derivative. Then we have minus h bar m omega ddx of x, then plus m omega h bar x ddx, and then plus m squared omega squared x squared, and then we have our f of x out here. So what you'll notice here, he did a nice little trick here, was go ahead and write that first one as a square, and then combine these guys. So we get this guy here, but then we get this guy becoming that term right there. So we have h bar m omega, the derivative of x times the function, minus h bar m omega x times the derivative of the function. So it is those two terms that really contribute to this extra term being present. So that's how we got that extra term out in there.